Before I show you a very 21st century way of dealing with logic using finite fields, I need to review briefly the axioms for a field. They're just the ordinary rules of arithmetic and algebra that you've known for years. For example, addition is commutative. A plus B equals B plus A. The order doesn't matter. Addition, furthermore, is associative. If you're adding A, B, and C, you can combine A and B first, or you can combine B and C first. There's an additive identity, generally goes by the name 0. It has the property that if you add 0 and A, or add A and 0, you get back A for any element of the field. Furthermore, in a field, every element has an additive inverse. If A is an element of a field, there's also an element that we usually denote by minus A, with the property that if you add minus A and A together in any order, you get 0. Multiplication, like addition, is associative. Multiplication, like addition, is commutative. That's sufficient, you might have noticed, to guarantee that 2 by 2 matrices, where multiplication is not necessarily commutative, do not form a field. There's a multiplicative identity whose usual name is 1. It has the property that if you take any element of the field and multiply it by 1, you get back the A that you started with. Crucial property, with the sole exception of 0, every element of a field has a multiplicative inverse, denoted by A superscript minus 1, with the property that if you multiply A inverse by A, you get 1. This means that the integers don't form a field because, for example, 2 does not have an inverse that is an integer. It's true that 2 has an inverse, the rational number 1/2, and the rational numbers form a field, but the integers do not. And finally, there's a crucial relationship between addition and multiplication that goes by the name of the distributive law. The nice thing about these field axioms is everyone knows them. You don't have to learn any new abstract algebra. And in particular, you don't have to learn all the rules that you would need to learn if you wanted to master Boolean algebra. Every field has the additive identity and the multiplicative identity. And in fact, there's a field that contains those two elements and nothing else. It goes by the name of Z2. And the rule for doing arithmetic in Z2 is simply after you add or multiply, you divide by 2 and keep the remainder. And this only changes the answer from ordinary arithmetic in one case, namely where you're adding 1 to 1. 2 is not in the field, but 1 plus 1 leaves a remainder of 0 when you divide it by 2, so 1 plus 1 equals 0. The way we're going to do logic using Z2 is to decree that 0 represents false and 1 represents true. It's possible to do this the other way round, but this is the more conventional approach. The addition facts, well, the only one that changed, I showed you 1 plus 1 equals 0. And notice when you add 1 to 0, you change 0 into 1. When you add 1 to 1, you change 1 to 0. So adding 1 converts true into false, false into true. That means that adding 1 represents the not operation. Because 1 plus 1 equals 0, every element in the field Z2 is its own additive inverse, and this applies even to something that you know only as an algebraic quantity. You can always replace minus A by A. Anytime you see A plus A, you can replace it by 0. This is going to simplify computation immensely. The multiplication facts are the same as for the integers 0 and 1. And it's important to notice that both for 0 and 1, A squared equals A. so you don't have to worry about any exponents that are bigger than 1, and a times 1 plus a is equal to 0. These are other rules that you can use to simplify computation. Otherwise, just use the rules of ordinary algebra. So now the subject we've been calling logic is the study of functions from z2n to z2. That is, from n-component vectors with elements in z2 to z2. And we'll start out with the case where n equals 2. We have a function f of p and q, takes a two-component vector whose components are either 0 or 1, and produces something that's either 0 or 1. And if we want to figure out what formula of Boolean algebra it corresponds to, we just substitute in 0 and 1 in all possible ways. That is, we write out the truth table. So let's do that. Here is p. Here is 1 plus p. You recognize, I trust, the truth table for not. This one is a bit less obvious. P plus q plus pq. Well, p plus q plus pq is equal to 1 in the case where p and q are both equal to 1. If one of p and q is 1 and the other is 0, we get 1. If they're both 0, however, we get 0. And this is a familiar truth table. It's the truth table for OR. Much simpler, the operation of multiplying p and q generates the truth table for AND. It produces 1 only in the case where p and q are both 1. So now we figured out how to convert NOT, OR, and AND into finite field computations. Other important operations are implies, and you will recall that P implies Q is true except in the case where P is true and Q is false. We can replicate the result of that operation by adding together 1 plus P plus PQ. That's going to give us 1 here. The 1 plus P will give us 0 here. And 1 plus P plus PQ is going to give us 1 in both the cases where P is equal to 0. Finally, P plus Q generates exclusive OR. If P and Q are equal, then P plus Q is equal to 0, which is equivalent to false, so we get 1 equivalent to true only in the case where P and Q have different truth values. A reasonable question to ask is, how many functions like this are there? Well, let's think of the two-variable case. You've seen lots of 4-row truth tables for functions of two logical variables. Since in the results column of that truth table you can have true or false in any of the 4 positions, there are 2 to the 4th or 16 possible truth tables. If we're forming a function of P and Q, there are no exponents greater than 1, so the possible functions are 1, P, Q, and PQ, each with a coefficient that could be 1 or could be 0. Therefore, there are 2 to the 4th or 16 possible functions. That means it's possible that there's a bijection between the truth tables and the functions. That, in fact, is going to turn out to be the case. And it will work with more variables. With 3 variables, you've got a truth table with 8 rows, and there are 2 to the 8th, which is equal to 256 possible truth tables. If you express this operation in terms of algebraic operations on P, Q, and R, since there are no exponents greater than 1, there are 8 possible terms, and 8 possible coefficients, each of which can be either 0 or 1. In other words, there are 256 possible functions. And this generalizes in an obvious way to any number of variables. So how do we prove theorems of logic with finite fields? Well, first case is a logical expression could be a tautology. A tautology is a logical function that's true independent of its input values. In other words, it's a function whose value is always true, i.e. 1. So, the way you detect a tautology using finite fields is you simplify. If the expression simplifies to 1, it's a tautology. If you have two logical expressions involving p and q that are equivalent to one another, that describe the same function, then they are of course represented by exactly the same function from z2, the space of two component vectors, to z2. And since anything plus itself equals 0, an easy way to test whether two logical expressions are equivalent is just add them together algebraically, simplify. If the sum simplifies to 0, that meant they were equal to one another. A few very easy examples. P or not P is a tautology. That is, whatever P may be, either it's true or it's false. You can verify this with the truth table. In the truth table, the results column contains nothing but truths. If we want to do this with finite fields, we say we have to have the OR of P with not P, which is 1 plus P. And since the generic way of doing OR is P plus Q plus P times Q, we add on the term P times 1 minus P. Now we have P plus 1 plus P plus P plus P squared, but P squared is equal to P, and when we look at what we've got a 1 and 4 P's. An even number of P's adds to 0. We end up with 1, proving we've got a tautology. We could easily use a truth table to prove the De Morgan's law that says that not P and Q is the same thing as not P or not Q. This came up in the discussion of NAND gates earlier. Let's do the same computation in Z2. Okay. Not P or Q. Not, add on 1. P or Q, P plus Q plus PQ. Not P and not Q, just multiply together 1 plus P, which is the negation of P, and 1 plus Q, the negation of Q. Multiply everything out, 1 plus P plus Q plus PQ, and what do you know? Everything shows up twice. The sum is equal to 0, which proves that the two expressions are equivalent. Earlier we used an 8-row truth table to prove that OR is distributive with respect to AND. In other words, we can put the OR operation separately with Q and R and AND them together. The other distributive law is also true in Boolean algebra. Namely, if I take P and AND it with Q or R, I can get the same result by taking the OR of P and Q and P and R. In order to prove this, I just have to show that the sum of the left-hand side and the right-hand side expressed in finite field notation is 0. Left-hand side, P and, that is, multiply P by Q or R, Q plus R plus QR. Add on to that P and Q, which is PQ, PR, which is P and R, and then since we're taking the OR of these, we have to multiply them together. But of course, when we multiply PQ by PR, we can replace the p squared by p, and when you multiply everything out, you discover the terms cancel out in pairs. We get 0, which completes the proof. Now let me try to convince you that there is a bijection between the truth tables and the Z2 functions. If you start with the function and need the truth table, this is purely mechanical. All you have to do is plug in the appropriate values 0 and 1 and do arithmetic to generate the truth table. Converting this into a Boolean expression is, in general, much more difficult, mainly because there are lots of different Boolean expressions that correspond to a given truth table. Every once in a while you luck out and can factor. For example, if I ask you, interpret 1 plus p plus q plus pq, you might say, oh, that's 1 plus p times 1 plus q. In other words, not p multiplied by not q, and therefore this represents not p and not q. You can confirm the answer by reconstructing the truth table. For each pair of values of p and q, you evaluate 1 plus p plus q plus pq, and you compare with the truth table for not p and not q. 0 matches up with false, 1 matches up with true. Here's a more systematic way. You now know how to convert a truth table into either disjunctive or conjunctive normal form, and you know how to convert a Boolean expression into finite field notation. If you follow one operation by the other, this will always work. When you're doing this as a practical matter, you look at the truth table to see whether the number of true rows is larger, which argues for disjunctive, or the number of false rows is larger, which argues for conjunctive. Here we've got only 3 true rows, and everyone prefers disjunctive anyway. We convert the second row into p and q and not r, the 5th row into not p and q and r, the 7th row into not p and not q and r, or them all together. Then crank out this rather messy OR of all these things, and eventually we end up with r plus pq plus pr plus pqr. Here's a truth table confirmation that I got that right, but it turns out there's a much better way to convert a truth table to a function, which I stumbled across quite by accident last month. You can look at the truth table and find out the coefficient of any individual term. I'll give you the rule and leave it to you to figure out exactly why this works. If you want the coefficient of a term with only one factor like p, what you do is look at the rows in the truth table where the other variables are all false. In row 4 and row 8, q and r are both false, and then you look at the truth values in those rows. They're 0 and 0. You add them up. If their sum is 0, the coefficient 0. If their sum is 1, the coefficient is 1. If we do the same thing with r, we look at the 2 rows where p and q are both false. In those 2 rows we have a 1 and a 0, and therefore the coefficient of r is going to be 1. What about a term like pq? Well, the only other variable is r, so we look at the 4 rows where r is 0. We see 1, 0, 0, 0. the sum is 1, so the coefficient of PQ is 1. If, on the other hand, you look at QR, you need to investigate all the rows where P is equal to 0, and the sum of the truth values for those is 0. Finally, for the coefficient of 1, you need to sum over all rows where the variables are all false. That's just the last row, so you get 0. And for the coefficient of PQR, you sum over all the truth values. There's an odd number of them, so you get 1. That reconstructs my R plus PQ plus PR plus PQR. And now here is another shiny app that does this. Let's see if I can get this right on the first try. I click that button and generate a random fourth column, F1, and my challenge is to write a formula that will produce that column. For the coefficient of 1, we use row 8 where everything's false, so that coefficient is 0. For the coefficient of P, we look at rows where Q and R are both equal to 0 and see 2 zeros, so we don't need a P. For Q, we use rows 6 and 8 and get a 1. For R, we look at where P and Q are both 0 and get a 0. For P times Q, we look where R is 0, 1, 0, 1, 0. That's another nice coefficient of 0. For P times R, we look at the rows where Q is 0, 0, 0, 0, 0. For Q times R, we use 5, 6, 7, 8. My goodness, this is easy. We get another 0. And for P times Q times R, we use all 8 rows. There are 4 ones there. Oh, this was obvious all along, wasn't it? This formula is Q. I test it, and I see that I've got it right. We can play around with this more at question time after class. And if you want to practice, just push the button, generate a new random column, and see if you can type in the right formula. When you're doing that, remember that to multiply, you need a star in order for R to do the evaluation correctly. So one last calculation. I think the most famous logical proposition of all is Socrates is a man and all men are mortal together imply Socrates is mortal. This is an example of a so-called syllogism. And here we have 3 propositions. The first one is P implies Q. Being Socrates implies being a man, and we know the expression for that. It's 1 plus P plus PQ. Next, all men are mortal. Q implies R. Manhood implies mortality, and that's represented by 1 plus Q plus QR. And the conclusion is Socrates is mortal. Being Socrates implies mortality. That's 1 plus P plus PR. And the claim is the first of these and the second of these together imply the third one. Okay, so we have to prove that F and G implies H. Let's start out with F and G. F is 1 plus P plus PQ. G is 1 plus Q plus QR. And you now think, I can subcontract this to an 11-year-old. You multiply this out, replace p squared by p when it turns up because there are no exponents greater than 1. And you get an expression involving 5 terms. Step 2. F and G implies H is the same thing as not F and G or H. Well, not F and G is something we're anxious to do because by adding 1, we just eliminate the first term here. There's P plus Q plus PQ plus PR. And then we have to OR that with H. H is 1 plus P plus PR. And because we're doing an OR, we have to add on the product of these two things. I won't bore you with the algebra, but when you calculate this all out, it turns out to have the value 1, and that proves that we've got a tautology, something that's obviously true in all cases, and that completes our proof. And in fact, that completes this introduction to the use of finite fields to do Boolean algebra.